We have learned that a statement is a sentence that is either true or false, and that quantified statements contain words like some, all, and no. In section 3.1.2, we're going to examine equivalent quantified statements. Now, in the English language, there are several ways to express one particular thought. And if we have a quantifier, there's equivalent ways that are constructed differently that still express the same idea. There's patterns associated with this type of language, and we're going to examine those patterns. So in the table below, we're going to look at a statement that contains a quantifier, like all, some, or no, and we're going to express this relationship on a Venn diagram. Now, a Venn diagram that's applied to logical statements is also known as an Euler diagram, E-U-L-E-R, Euler diagram. So those are related techniques. It's like a Venn diagram for logical statements. So we're going to examine the relationship between those two sets on a Venn diagram and then form an equivalent way of stating the same thing. And we'll look at some specific examples. So the first statement we'll consider is all A are B. We're going to assume that this is our universal set in this rectangle, or our frame of reference. Now, if all A are B, then we have a set A in which every element of A also belongs to the set B. So A is completely contained within the circle B. Every point inside the circle A is also inside the circle B, so this allows us to spatially understand the relationship between those two sets. The statement all A are B is equivalent to the statement there are no A that are not B. Notice we have these words like no and not. Those are often associated with a negation, but in this case, they're expressing the same thing that all A are B expresses, just in a different way. So those two statements are equivalent. For example, all students are taking math. If I use this pattern to form an equivalent statement, I could say there are no students that are not taking math. So even though these two statements are worded differently, they're expressing logically the same thing. Look at the pattern. All students, we could say that's the group A, are taking math. That's the group B. And the pattern here, there are no students, there are no A that are not B. Those two are stating exactly the same thing. Let's try this with another quantifier. Some A are B. So we want to express the relationship between these two sets, or these two logical ideas, on our Venn diagram. The rectangle is the universal set, and we want to express some A are B. So I'm going to have set A, and we want to show that some A are B. So if I choose a point right here, those are elements in A that do not belong to B, but points in this region are elements that are in the set A that also belong to the set B. So we could say some A are B. That would be in the intersection of those two circles. An equivalent way to say this, there exists at least one A that is B. So what we want to do is take the patterns established by these two equivalent statements and apply it to a specific example. Statement number 1, some students are taking math. That statement fits this pattern. Some A are B. I want to rearrange this using this pattern. There exists at least one A that is B. So we would write it, there exists at least one student that is taking math. So we have the pattern, there exists at least one. Here's my group A. that is taking math group B. So those two statements, even though they are worded differently, express exactly the same thought. There's a lot of variation possible in language, and so we want to recognize that there's different ways to express the same idea so that later when we codify this or write it in symbolic form, we can recognize those equivalencies. Let's look at our third quantifier, no A or B. If we express the relationship between A and B in this case, they're going to be disjoint sets. There's no overlap between those two circles. Another way to say this, all A are not B. So every point inside circle A is not inside circle B. Let's take these patterns and associate it with a specific example. The first statement fits this pattern, no A or B. No students A are B taking math. We want to form an equivalent statement using this pattern. All A, that would be students, are not B, not taking math. So we have this pattern. All students A are not B. So those two statements express exactly the same logical thought, even though they're constructed a little bit differently. They're using two different quantifiers, no and all, but they're stating the same thing. Let's look at one more example here. Some A are not B. Now, we've already looked at some A are B, so I want you to look at the relationship between some A are B and some A are not B. It sounds like we're forming the negation, right? Some A are B seems like it could be negated by inserting the word not. Some A are not B. But notice on the Venn diagram that the relationship between these two sets is exactly the same. In this example, the some A that are B live in the intersection, but over here, some A are not B, they happen to live out here, but the relationship between the two sets is the same. So saying some A are B is equivalent to saying some A are not B. Now, this is also equivalent to the statement not all A are B. Whoops, typo, sorry about that. Not all A are B. So let's apply this to our example. Starting with this pattern, some A are not B. Some students are not taking math. That's B. And we're going to re-express that using this pattern. Not all A, that's not all students, are B taking math. So not all A, not all students, are B taking math. So in this section, we were examining quantified statements and their equivalent forms. In the next section, we'll learn how to negate quantified statements, and we'll review this pattern as well.